Here we have a couple 2D kinematics or projectile motion problems. All right, number 1 says, a projectile is launched at ground level with an initial speed of 50 meters per second at an angle of 30 degrees above the horizontal. It strikes a target above the ground 3 seconds later. What are the x and y distances from where the projectile was launched to where it lands? So the first step should always be to draw a picture. Alright, just have a visualization of what's going on. I'm starting way to the left here to give myself some space. So let's draw maybe the ground a little ways. Our projectile launching at 30 degrees. Maybe this is V initial. And it's going to travel some distance and hit a target mid-air. Okay, we can break up the velocity into x and y components. Okay, so this is initial x and initial y. And we should identify what are we solving for. So we do that here. It says find x final and y final. Okay, so we can write down the things that we know. So let's draw a little line here. I'm going to label the known values in the x direction first. Our initial position we can call 0 meters. Final position is what we're solving for, so I'll leave that. There is no acceleration in the x direction. I'm not going to label it here. It just means it's uniform motion in that direction. Right? So the only other really interesting thing in the x direction is the velocity, which is actually a constant. Right? And we can use some trig to find this. Remember, v initial here from the problem is 50 meters per second. So v initial x is 50 meters per second times a cosine of 30 degrees. And if you do that math, I think you come up with 43.3 meters per second. So those are known values in the x direction. And we can write our known values in the y direction. So our y initial is 0, y final is what we're looking for. The acceleration in the y direction is minus 9.8 meters per second squared. And the initial y velocity, so v initial y, is v initial times sine of 30. If you do that math, I think you end up with 25 meters per second. Right, so the other thing we're given here is the time that this takes, and it's actually the same time for each motion, x and y, right? Time is the thing that connects these two motions together. So delta t here, which is kind of off by itself, is 3 seconds. Okay. So now we've identified the things that we know, and we know what we're solving for, so now we can look at our equations and determine what equations are going to solve for the unknowns, or for the interesting values here. Alright, so the x direction only has one equation, and we actually have everything we need to solve it. We know the velocity, we know the time, and we know where it started, so we can figure out where it ended. Right? So x final equals x initial plus vx times delta t. Plugging in some numbers. And if you do that math, think you end up with 129.9 meters. So x final is rounded to 3 sig figs, 130 meters. We could put a decimal just so we know that it's 3 sig figs. Okay, so that's one of the things we're looking for. The other one is the final y value, and we actually have everything we need to find that as well. We have y initial, we have v initial, and we have delta t. So the equation is y final equals, oops, so plugging values into this, 0 meters, doing that math, I think gets you 30.9 meters. Y final. And those both seem pretty reasonable. Okay, we could double check this by maybe solving for various values through this motion. It looks like we're maybe past the peak, although we may be before the peak. So I suppose you could just solve for where the peak is and see where these fall. But again, they seem reasonable. So the second problem here says, suppose a soccer player kicks the ball from a distance 30 meters toward the goal. Find the initial speed of the ball if it just passes over the goal 2.4 meters above the ground, given the initial direction to be 40 degrees above the horizontal. So we'll draw a picture again. And maybe draw the ground. With this kicked at 40 degrees, so it's nearly equal x and y velocities. Okay, we can draw a goal over here, maybe right here. And the trajectory of this ball. Something like this. Right, so this height is 2.4 meters. The distance here in the x direction is 30 meters. And again, maybe it's useful to break this velocity. So this is a v initial, and that velocity can be broken into v initial y and v initial x. So it's interesting here to point out that I've written down v initial y and v initial x, but I don't actually know v initial. Actually, that's what I'm solving for, right? Find v initial. And that's okay, I can still write v initial y and v initial x. Just recognize that I can't put a number in when I do this. I have to leave it as v initial cosine 40 or v initial sine 40. So let's proceed. So the known values in the x direction, I'm starting at the origin. Actually, no, x final. I'm going to 30 meters. And I can write down an expression for v sub x. Looks like it's going to be v initial cosine 40. I'm going to leave this as a cosine 40. I could write it as 0.766, but I think it's going to be more convenient to leave it as cosine 40. So that's in the x direction. Let's make line here, the known values in the y direction, we can call y initial 0, y final looks like 2.4 meters, and say v initial in the y direction is v initial times sine of 40. Right, we also know the acceleration is minus 9.8 meters per second squared. Okay, so we don't know v initial, that's what we're looking for. We also don't know time, and it seems like time is something we're going to need. Now we can't solve time numerically, but we can, from the x direction, find a semi-simple expression for time. Okay, so let's find delta t in terms of v initial. We're going to do this using the x direction. Right? So simply put, we can say x final equals x initial plus vx delta t. Alright, we can plug in 30 meters equals 0 meters plus v initial. V initial in the x direction has this cosine 40 on it, cosine 40 times a delta t. So I can write an expression for delta t. I'm going to do it right here. That is 30 divided by v initial cosine 40. 30 meters divided by v initial cosine 40. Okay, that's going to be useful in a minute, because now I can take that expression, this expression for the time it takes to get to this position, and I can plug that, let's give ourselves another line here, into an equation for y direction motion. Okay, we have a y final and a y initial, an expression for the velocity in terms of the v initial we're solving for, and an expression for delta t that also has that v initial in it. So I'm heading toward one equation, one unknown. It's going to be a little complicated, but that's okay. So let's write our equation. Y final equals y initial, v initial y delta t, half ay delta t squared. I can plug some numbers in. That's 2.4 equals 0. Again, the expression for v initial y here has a sine 40 in it, so that's v initial sine 40. And then delta t is this 30 over v initial cosine 40, so that's 30 divided by v initial cosine 40. And I'm going to have to write the next bit on the next line here. So I also have a minus 9.8 over 2 times 30 over v initial cosine 40. Okay, so these two are all one line. So I'm going to simplify that a little bit. Looks like v initial and v initial in the second term cancel out. Sine 40 over cosine 40 is tangent 40. Okay, it's not super critical that you rewrite it that way, but it's going to make it more convenient, and again, I like it better than carrying a bunch of decimals around. So I'll rewrite that in that way. I figured out a square on the delta t next to the 9.8 over 2. So let's rewrite this again. Let's give it another line. Looks like 2.4 meters equals 30 times tangent 40 minus, this is a 4.9 times 30 over v initial cosine 40 squared. Okay, so if I subtract this over, I think I end up with minus 22.773. I can divide this 4.9 over and the negative, and that gives me this expression is equal to 30 over v initial cosine 40 all squared. Okay, and now I can square the right-hand fraction. I could cross multiply and solve for v initial. Okay, so I'm not going to do that because I'm running out of space here, and at this point it's just algebra. So the v initial here turns out to be, I think, 18.2 meters per second. Okay, and you notice we didn't have to think about going from the x component or the y component to the full v initial because we did that when we plugged in at this point and when we plugged in at this point. Alright, so it gave us some messy algebra, but it was just algebra. If we're careful enough, we can follow it through.